Hi guys, as Ian mentioned, my name's Bradley. I work quite closely with Alberto and Raina from here in the office. Today I'm going to discuss nonlinearities, particularly structural nonlinearities, and why we don't really use them and how we can kind of exploit them more than we currently do. So what do we mean by nonlinearities? Well, in terms of structures, what we mean is when we apply a load to a structure, we want to see a nonlinear response to that. So the stiffness could increase on that structure, and therefore the displacement would reduce, and suddenly we could get a critical point at which the stiffness is zero. We get a singularity in our stiffness matrix, and we'll get a snap through, a sudden large deformation without any significant increase in load. So these can be like buckling, snap-through structures, etc. So why do we currently avoid them? Well, they're not really taught at undergrad level, so when people move out into industry, some of them aren't even aware of them. But mainly, it's because of these 3 points here. They're very complicated to evaluate, so we don't have the best closed-form solutions to deal with these. We do really need finite element to solve a lot of these problems. But then, even that in its own right, the tools that we use to solve these nonlinear finite elements are not actually good enough currently. And finally, the general mistrust of engineers. As soon as we see any form of nonlinearity, we seem to think that it's some form of failure that's occurring. So why should we be actually utilizing these nonlinearities or nonlinear structures more so? Well, there's a wide range of applications mainly. These can be from a very, very small scale, like MEMS, for example, to large scales, morphing wing structures and what have you. And what I'll show also is we can actually improve the structural efficiencies if we do utilize these nonlinearities. So a case study we've been working on recently is this simple frame structure. So at the top right there, you can see the undeformed shape of the structure, where all we've got is a simple load being applied at this bottom point here, and it's a simply supported structure. There is no rotation, no free rotation in each of these joints, so it's a frame, not a truss. What we have here then is the load displacement response from the point at which the load is being applied. So you've got displacement along the x-axis and load along the y. If we use a conventional RIX solver, which is what you'd get in your commercial codes, you would potentially just solve this top curve. Now, as you can see there, the red line suggests an unstable region, so that's physically not attainable. We will never see that in this structure. What will actually happen, it'll follow, from this bifurcation point, it'll follow this bifurcated path, and the blue lines are the stable regions which we can physically use. But, that being said, there is this stable region at the top, which is therefore not being exploited. How can we actually close that gap? How can we travel up this line from this point here and travel up to this point instead? Well, looking at these mode shapes on the right-hand side, these deformation shapes, so for the fundamental path, we have this shape. It's a symmetric shape. And for this natural path, or I say natural because this is the path that the structure will naturally follow, we have a symmetry breaking shape. So we need to close this region here, and we've successfully managed to do that by using this solution method we're using to solve our nonlinear finite elements, which is generalized path following. So the way we're doing this is we're taking the shape from one of this path at the top. We're taking any point along that. We're taking this deformed shape, and then we're using it as a perturbation in the third dimension, and that becomes our parameter. So here is just, this axis here is our alpha, which is just a scaling factor for the actual displacements we've used. And as you can see, you get to a certain point at the top there where this red area disappears up here. We therefore gain the full structural efficiencies of the top curve, increasing our load carrying capacity. So where does this lead us? Well, we've successfully done it with that structure, and we thought, well, what happens if we kind of evaluate some other structures? We found something else quite interesting. This is something we've never seen in literature before. These are unconnected fundamental paths. So you'll have a symmetric solution up here on the blue solution, which again, is stable, but this is what you'd see in reality. You'd get up here, and you might snap across there if it doesn't go into the plastic range. So this is something else we're looking into. How can we now bridge this gap? How can we utilize this stable region up here? And as you can see, the deformations are huge. So we can potentially exploit some really cool structures using this technique. So if you want to kind of hear more about this, come and find me at my poster, and I'll explain it all in a bit more detail. But for now, thank you for listening.